All right, here you go. Thrill of a lifetime. Anybody done the zipper? You can look forward to doing it after this course. Now that you're have a full understanding of it and what it does to you. The zipper ride, we've got 12 cars, I think it is, on the zipper ride. Very simple design. You've got two wheels that spin together, and you've got a cable that's connected around those two wheels. And of course, those two wheels have a boom. Those two wheels on the end of a boom. And so the cable just goes around the boom and those two wheels. Cage is attached to that cable. So basically you're just going up and down along this boom. But they do put in one twist, one turn, or actually a few turns. Anyway, they rotate the boom while you're moving along the cable, okay? We would like to know, you have a support pin, pivot pin that holds the cage on a fence. Fence is basically a truss structure. I would like to know the forces in that fence. Okay? To figure out forces during the 2-minute ride, it's a 2-minute ride, what do I need to know about what's going on at the pin? Force is proportional to what? Proportional to acceleration. So the project assignment is figure out the acceleration of that support pin for the 2 minutes of the ride. So here's, of course, your assignment sheet. I did give it to you in the Word document and PDF document, so you can use it, whichever version you have or that you prefer. So let's go ahead and look at this particular figure here. You have the different dimensions of it. This is how they load you up. You start down here, as we call it, as C0. Load you in the cage. And then they, of course, move it around to get the ride loaded. And so we're going to start saying, okay, that's your starting point. You start down here. Travel up 30.6 from down there. Then we have a radius of 3.3 feet. Okay? We have the distance out. The way the model is set up, we come out a certain distance and quote up a certain distance as a starting point. This is our height here, and this is our W/2. So we're saying our height is our 4.4 feet, and our width task 1 is, okay, analyze the motion of this point P. This is the pivot pin that we referred to. Figure out the position for that pin around the boom. Okay? That's what task 1 is. So you see that we have it divided into different zones. Depending on whether you're on the straightaway between the two wheels or whether you're going around the wheel. So we've got zone 1, zone 2, zone 3, zone 4. Try to understand what's going on with our motion. Right now, we're just going to track the position. Of course, we're going to get this position as a function of time. So you'll see what we're referring to is point A and point P. Point A is where it's attached to the cable. Point P is how far the fence sticks out to where the pivot pin is. And so we'll be referring to RA and RP, figuring out both of these as a function of time. Okay? To do that, switch to a slightly different color. We're going to refer to the, we'll call it distance traveled as S, your S of T. Okay? So S of T for each of the zones. S1 as a function of time. What is going to determine the position of this as it travels along the cable? In zone 1, traveling straight between the two wheels, what's going to determine where that point is in the 2 minutes? What piece of information do you need to get about the ride? When he pulls that lever and starts the ride, he engages the cable, and it just travels at a constant speed, actually. The cable travels at a constant speed, and the boom rotates at a constant speed. The acceleration comes about because you're changing your, we'll call it, velocities, the direction of your velocities changes with time. Okay? That you have a velocity of the cable on your spec sheet that's available. The boom rotates 7.5 revolutions per minute. Cable rotates 4 revolutions per minute. So for me to figure out the velocity of the cable, V of C, 4 revolutions in a minute means how many revolutions in seconds? One revolution, let me write this way, 1 revolution in 15 seconds. That's what it takes. What is a revolution around this ride? If you start here, 1 revolution, how far did you travel? What is S in those 15 seconds? I'm saying, okay, your velocity is 1 revolution in 15 seconds. But what is that distance of a revolution? How far do you travel? You got 2 links, and you've got basically a circle. Plus 2 pi r, okay? What will be 15 seconds? That is a constant velocity. So your velocity, your distance traveled, we'll call it, as a function of time, is this velocity of the cable that you figure out times the time of the ride. Okay? That takes care of zone 1. Zone 2, I'm going to blow this up. This is point A. We're now going to measure when we're going around the wheel by this angle beta. Okay? What is that angle beta? And what is the function of that angle beta? With relationship to the velocity of the cable and time. So I need to get beta of t equal to something that involves that velocity. Is its radius r. So if you know the tangent velocity, vc, that you figure out here, what is beta t? Let me go ahead and, how fast does this angle change with respect to time? How do I take this tangential velocity for a circular path and translate it to an angular velocity? That's what we're trying to figure out, okay? You need to know how much this angle changes with respect to time when you're in zone 2. You know the tangent velocity, it's the velocity of the cable. It's a distance radius out from it. So to get the angular velocity, how fast this angle changes with respect to time, divide your tangent velocity by that radius for that circular path. So of course your VC over R times time gives you beta as a function of time, okay? So now that we've got, this is, I'm going to go ahead and switch this to my beta of t. That's what we're measuring there for zone 2. Now that we have both of those as a function of time, we can describe our positions. So this is your task 1A, S1 of t. If you want to, be clear that you're dealing in zone 2 now, it's very important that you keep things segmented into which zone you're in, because your equations change depending on which zone. So we'll say S for zone 1, beta for zone 2, S for zone 3, beta for zone 4. Okay? You're given your different, we'll call it position vectors. Your worksheet gives you your position vector for A, the attachment point to the cable, and also how it translates to the attachment point for the pivot pin, okay? So you know R of P, let's just focus on R of P, that is a function of this S of T and this beta of T, depending on which zone you're in, okay? So now that you have S of T and beta of T, fill in the table for your different time segments. Okay, put in what T is, figure out what your RA is in the X direction. This is what we're talking about, our XB and our YB. Okay? You're filling in this table for the 15 seconds it takes you to go around. My recommendation is when you start setting up these calculations, this is set up in quarter intervals between the 2 points. Basically, I divided this into 4. I suggest you divide it up into like 8ths or 16ths. Because when you plot it, when you get further down in the assignment, okay, you want to finer detail than just doing it in quarter intervals. Okay? What you fill in the table is just quarter intervals for the first 15 seconds. And of course, when you plot that out, what should you get? Your A is going to look like the boom, going around the perimeter of the boom. That's what it's supposed to look like. Your pivot pin, you'll see, has a slightly different shape when it gets to here. Because as soon as it gets to this point here and starts going around the wheel, it basically has to make a jump, because now I'm having to move around the wheel. So we have a discontinuity in it, and it gets back here, so okay, now I get caught back up, we'll call it, with the cable. So you'll see this, we'll call it, little kink in your motion due to the pivot pin. And that's really what creates the thrill for you when you get that acceleration going around the wheels, okay? Get that figured out, verify this is the kind of plot you get, and you're good to move on to stage 2. Stage 2, spin the boom. How does that change? How does that change your motion? Your motion around the boom stays just like you have it in stage 1. All you have to account for now is that the boom is rotating while you're moving around the boom. Okay? Position. You know you can express this is my inertial reference frame. We'll call it the horizontal, vertical with gravity, X and Y. But there's a, we'll call it when the boom is rotating, I have an XB and a YB. The XB is perpendicular to the boom. Y is, we'll call it along the length of the boom. And this is what's measuring theta. Okay? So I chose to set up my coordinate system. I'm going to go ahead and pick an arbitrary point out here. This is where A is. We come out here to P is. You have P. Expressed in terms of I need to move that off to the side. How far am I away from the center of the boom? The radial direction, which of course means there's also a theta direction. Okay? So this is what we got. We're saying that the location of the pivot pin with respect to the rotating boom is just some distance out from the origin, RPR, ER. I know this relationship here, magnitude, the length, the distance you are from the origin can be figured out by your two components in the X and Y. So you have these relationships that determine your position for the pivot pin with the rotating boom. Okay? So what you're doing is calculating. One thing to note here, when you start with the boom straight up at time 0, this angle theta is from the X to the XB, but your angle that you start with for theta P, your theta P naught, it starts down here. So you have an RP, R naught that you can figure out. And you have a theta P naught that you can figure out. When it's straight up, theta is 0. You're at a distance here that you can figure out, and you're at an angle there. So your starting point is not at 0, 0. That's what I'm getting to when you start things out. Okay? Start your time, start the ride. Fill in your table. For each of those time increments, how much did the boom rotate? Where did we get that? Where did we get theta dot? How fast did the boom rotate? We said earlier, 7.5 revolutions per minute. What is that equal to? This is your omega b. 7.5 revolutions per minute. But what is that in radians per second? How do you do conversion? I said 7.5 and I only wrote 7. 7.5 revolutions per minute. How many radians in a revolution? 2 pi radians. And of course, 1 minute has 60 seconds in it. So figure out your theta dot. Excuse me. You have your time intervals that you put in there for theta. Okay? Well, once you know theta, back up to here, you can figure out your R's. So knowing your theta p, and the only difference between theta and theta p is this starting point. You start at an initial location that's not at, we'll call it the level with x. It's down here at the bottom. So the initial angle that you start at. And that's the only difference between theta and theta p, is that initial starting point. Figure out your distance away from the origin at these time intervals. Now that you know theta, you can come back to these relationships here. Knowing what theta p is at that given time interval. You've got these relationships for zone 1 and zone 2 of what RP X, and RP Y are. This R plus H and this ST, and then your X and Y. So you have your terms there, so you can figure out what RPR is. Fill in your table for the 15 seconds. Task 2B is expand that for the 2 minutes. Okay? So you're going to do it 8 more times. So you get the first 15 seconds right. It's just a matter of copy and pasting. Okay, let's do another 15 seconds and another 15 seconds. Your theta keeps increasing as you keep going along, because it keeps spinning around. You don't get back to the same starting location until you get done with the ride at the end of the 2 minutes. And if you do it right, pass, 2B here, it's going to be a beautiful flower when you look at that pivot point and how it draws around the center of the boom. Never crosses the center, but you get this nice polar plot. Looks like a really pretty flower that shows your position for those 2 minutes. Okay? Knowing the position, how do you get velocity? Take the time derivative. Time derivative has already been done for you for this expression. You know what this expression is as a function of time. That's been figured out. But you got to figure out this RPX as a function of time in the area. That's what, We got to take the differential of this with respect to time. Okay? So when you came back to, let's go ahead and go back to here. So for task 3A, for each of these zones, take the time derivative of these expressions. Okay? So I'm going to have to write it up a little bit higher here. When you're on the straightaway, this portion right here, in the XB direction, does that position change with respect to time? The X component. R plus H. It's a constant number. So what does this work out to be? 0. What about the y? What changes in this expression with respect to time? Just s of t. And what is s of t? Velocity of the cable. Okay? So everything's fine and dandy as long as we're in zone 1. But when we get to zone 2, when we go around the wheel, now I got to take the time derivative of this one. But still, it's possible. What do you get? R plus h minus sine of beta t, beta dot. And then minus 0.5 w cosine of beta t. Beta dot, of course, what is beta dot? Is your VC of R that you had here, okay? Same thing with the Y. Here we have what, R plus H cosine of beta t, beta dot. And then plus 0.5 W. Actually, that'll be a minus now, because cosine is sine. And then again, beta dot. There. So you can pull out your beta dot, but you can take the time derivative. Get those expressions. Once again, figure it out. For your first 15 seconds, expand those calculations the rest of the 2-minute ride. Task 4 is a repeat. You took the time derivative of velocity, now take the time velocity. You took the time derivative of the position to get the velocity, now take the time derivative of the velocity to get the acceleration. So it repeats one more time. And of course, once we get our accelerations, we can equate those to the forces on it and figure out, make sure our fence is going to be strong enough to hold this crazy ride. Good enough to get started?